I mean, there's a curve. I drew it in the board, but it doesn't have to be coming down to the board. It could be a three-dimensional space. I think with that particular curve, the curvature value should be larger at A than B. Because I think if you move, say, one distance along the curve at A, or locally about A, then I think the tangent vector, the unit tangent vector, PR, is changing more rapidly than at B. If at B, locally speaking, I travel one unit on the curve. Remember, I'm parameterized in terms of the curve. And as a matter of fact, I think the curvature of B is going to be larger than the curvature of C, because the curve seems to be somewhat linear about that point that we're able to see. Linda, am I making sense?
But I understand K. So what's like? What would be a random? I mean, if you tell me the slope of a line is 4, I can picture what a slope of 4 looks like. What's the value of K that I can picture? I mean, obviously K gets close to 0 at C. And then
I can't even do it unless I were to redraw this picture very carefully in terms of the X, Y, Z coordinate system, unitized carefully.
But I'm just saying, just in general, what kind of values of K would like the curvature be?
And I can't answer the question. I can't because it depends on how we unitize my axes. I mean, what each unit represents. And in addition to that,
are we going to see values of 100 or 2,000 or for these curvature
oh, I
values?
see.
Just absolute numbers. What are they going to look like?
You're not going to yell at me?
No.
0 to infinity.
Okay. But
They won't have any.
like a line, the slope of a line.
Yes,
0
very
to
much.
But in our experience with kind of things that we can actually see and not have curves so tight that you can't even tell the difference.
True, yeah.
Okay, so
And you know, numbers you're going to come up with are, I hope are like really pretty ones, like the natural log of 1317.
okay, so
It's just the bigger it is, the tighter curve we have.
okay. We're gonna see
But the
values-
range is from 0 to 100.
Yeah, but we're going to see values less than 50 in general with the work we're doing.
That's fine.
I don't know. I don't have a feel for K yet.
Are we going to be really honest with you?
Okay.
Because when I write my testing questions or my quiz questions, I don't even care about it.
Right.
So, can I ask a question?
Yeah. So they're talking about opponent's acceleration here, which we also talked about in physics, but we use different formulas to get that. That was in square space, not cube space. So is that more generalized formula, like for every?
Yeah, can you tell me how you did it in physics?
We use. Can I write it on the board?
Yes, please. Help us out.
Okay, we use like, because this is radial. We use like acceleration radial was v squared tangential over the radius, and then the a tangential was just the derivative of that. It was like dv and I think over dt. I think that's what it was.
And what do you mean by radial distance? You mean you're emanating from a point, a fixed point, and moving outwards?
Yeah, it was because our problem consisted of like that, and then find like your radial acceleration that way, and then tangential acceleration. And that's how we sort of talk about components of acceleration on like a circle, but this is more complex in terms of a curve, not a circle.
So, can you do this for me? Is that P for velocity?
Yeah.
Tangential velocity.
Oh, it's the magnitude.
Tangential velocity around the circle.
Okay, here's what you've done then. Neither one of these is specifically acceleration. It's just a component of it.
Yeah.
It's sort of like saying, I got an acceleration vector here, but oh shoot, let's talk about the horizontal component and the vertical component. Or maybe we usually take a tangential component, a normal component, which by the way is something I want to discuss today anyways. So I think you're not violating my definition. I don't think you're different. It's just that you're looking at smaller portions of acceleration. If acceleration is going this way, you're looking at a portion that's going in a different direction. And so I do think it's a different definition. You just broke it up in a different fashion.
Yeah.
Because I think all of us were gonna have the same concept of what curvature really means.
Okay.
Is that helping, Matthew?
Yeah, because I was asking because because they did the same thing that we did in physics. They have acceleration equals the normal plus tangential, but they sort of like for a normal equals.
What class do you see that in, by the way?
Huh?
What class do you see this in?
Physics 4A.
Oh.
205.
Well, how do you prove it?
You don't. They just give it to you.
They
Really?
Yeah. It's pretty bad.
You prove it.
But I thought 4A, the 4 series was a calculus sequence.
yeah, they proved a little bit.
I remember doing a proof and then verifying it with some experiment.
Because to prove the A tangential, they said that it was the change in the direction of the velocity.
No, I understand completely. You're declaring that's what it is. And by the way, it looks like that. And by the way, it looks like that sounds like math magic.
Yeah.
When we find out the curvature of a line, is that only relative to that line, or is it relative to all lines?
Well, all lines have the same curvature. So,
Okay.
did you mean curve?
Yeah, that's
Sorry.
So,
Can you say it again? I'm sorry.
okay, so if we take the curvature of a curve,
Yes.
you happy?
Yes.
Is that curvature value only dependent on said curve, or is it a universal for all curves?
It's only for the said curve, and worse than that, it's only said for that one point on that curve.
Really?
Well, look at this curve. I think curves are changing depending where you are.
Oh,
I would totally agree, but how do I see that pen?
Yes.
What I'm asking doesn't make sense unless I draw it. Okay, so.
You guys are always asking really good questions.
So this is our imaginary line.
What are you trying to write there?
It's a line or a curve. Okay, so we have point 1 and point 2,
Yes.
and then we have A and B. So this is going to have that f of x blah 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 function, and then as soon as you plug t into this value, it's going to give you, or whatever. As soon as you plug parameter into this value, it's going to give you a magic number that says its curvature along this area is that. And then you're going to get this one that's going to say its curvature along this area is that. Now for T1, let's call this, and T2 right here, could you say that these two lines, one is relatively more curvy than the other?
Yes, as long as you're in the same coordinate system.
Oh, okay. I was just wondering.
Yeah. Very much so.
so you can use the curvature value you obtain from one section of one line and compare it to the curvature value of a line section of another line or whatever, and you can compare those two values even if they're different functions, different dimensions, that sort of thing.
That's exactly what I was asking.
Number, I gotta confess, with this thing that I derived last time, where is it?
It's on middle bottom, like curvature equals k, blah, blah, blah. To your left, up, okay, come on. So
Sorry.
It crossed me over.
It's Friday, okay? You guys have to confess, doesn't it look like this? Really? What's that?
I'm looking in my book.
What book is that?
I don't know, I don't have it in front of it.
But it's a different textbook. you mean.
Yeah.
Gotcha.
And they have these different subsequent, more definitions, but.
That's what I was saying earlier. I mean, usually when I teach this course, I have more versions of this as well.
They're doing stuff like that, and we have, what, I don't even understand what they're saying, double part, and I do the letter S.
Okay, now hold a thought before you go to the next page. Hold a thought. In her book, she's got this. But when you look at what I derived in class, that's curvature described in terms of the t parameter. Whereas when you have this described in terms of the actual distance on the curve, which is how I defined it. But my consequence, if I could get a useful formula, was this in terms of t.
So what are they saying?
They're saying they're describing the curvature solely in terms of how much distance to travel on the curve, which is s. They've got parameterization in terms of the curve, whereas I've got parameterization in terms of t. And so think of this k as a function of t with what I have on the board, but with what I see in that page in your book, You've got the curvature described in terms of a whole different variable. And that's why it looks different. Think about it, watch.
Well, that seems simple.
What's that?
Like, how do you even, how?
No, that's not simple. I think what you see in your paper is miserable in terms of computations, because you're gonna have to take your R bar T and re-parameterize it. And rewrite it in terms of R bar of something else.
How do you even do that? Well, I mean,
I can show you. You just compute the arc length function curve that looks like this. If I'm not getting too sloppy, you guys, I'm trying to write fast. And now use this as the input of your function instead of t. I think it's a lot of work. That's why that author, whoever he is probably very much like me and saying, well, once I've got that, let's pay the consequence. It's just too difficult to work with. And now turn the page and let me see if you've got other forms compared to what I have. Oh, I'll get that.
It's all
I just-
S, though. Look at that. T down here.
These are my normal vector.
Oh,
Even that doesn't have quite as many as I would like. And when you're looking at the B things and the big N things, that isn't really related to the curvature right now. I mean, when we use curvature to generate those things.
so it's confusing me, so sorry.
Yeah, I think it is. But I'll talk about the B things and things today. It'd be similar to what I think Eric or Matthew brought up in terms of breaking acceleration up into different components. I'll play the same game.
In the book, they in 11.9, I think it is, they actually have you solve, do that right there. Is that they have you do the integral and carry out and plug that back in to the
Yeah.
parameter.
Do you see how much work it is?
Yeah.
It's a bit of work.
The K value is, I mean, it tells you the magnitude of the curves of that curve, but is that gonna tell us anything about direction?
No.
Or where it's going, like it could curve this way or it could curve that
No.
way? So
No. Good question. So maybe as my curve is going through space, curvature may not be incorporating that notion of direction, but we could do this. As my curve's going through space, maybe we could talk about the plane to which my curve's tangent line at any given point is normal. I could do something like that. I'll do it today, actually.
Assuming we have enough time.
I'm confused. When you talk about S, I'm thinking of a length, a number of points, but T I feel like is just one single point, like instantaneous curvature. I don't know what you want to call it. Oh, we're talking about a range on a curve, right?
I disagree. Let me put it this way. And let's take the two space so I can actually draw it. X-axis. No. T-axis. Y-axis. Oh, we'll get rid of purple. It's not working. And let me talk about this curve. And let's talk about this position on the t-axis. In this position. Do you guys agree that moving from this point to this point, my parameter t changed by 1 unit? And look at the distance I traveled on the curve. It's some distance which clearly is bigger than 1, isn't it? If I just drew a nifty little right triangle, I think the curve's length is approximately the length of the hypotenuse of that right triangle, which is clearly is going to be larger than any of its legs and lengths. So I think the distance traveled on the curve from point to point is bigger than 1 unit. And so I can talk about how much money I earn as I trace this curve as I increase by 1 unit in terms of t. And I think the amount of money I earn is some quantity. Let's say $20. But what if I reparameterize in terms of curvature? Well, I misspoke. What if I reparameterize in terms of arc length? Then I think as I'm grabbing money, traveling one distance at a time, I think to travel one distance is going to be traveling from this point only to maybe this point. And I'll be earning less money than $20. Because now I'm parameterizing in terms of arc length in green, whereas in black I was parameterizing in terms of my parameter t. And so I think what I'm throwing in my pocket in terms of money is completely different in both cases. It's a different parameterization.
And you like in terms of T because it's usually bigger.
Thank you. Well put. So then I have to do all that work that you would have to do in that book in terms of converting everything in terms of S's, not T's. Don't take it the wrong way. I'm not saying every time it's so difficult. I can create easy case scenarios, I'm just saying in general, it would be a lengthy process, in general. And I bet, if there are exercises in the book having you do that, in your book, I bet there's very few exercises.
But let's say that S is easy to compute,
Yes.
then I'd probably be better way to go.
In the end, you're gonna get the same number. That curvature value is not gonna change. Matthew, you have a question?
can you use the curvature at like different points to see if two curves are parallel to each other? Like,
You mean if they match each other's movements?
Yeah, something like that.
No, because curvature is an absolute value, so
Yeah.
you're going opposite directions as well.
Yeah,
okay.
I don't think that'd be safe at all.
Is there ever a case where you have non-linear, where you have curves that are parallel to each other? Is there ever a case where you can say that, or do you have to have straight lines
Sure,
in order to?
here's an easy example, look at your double helix.
Mhm.
There's such a plan.
Okay, but it's not through curvature that we're gonna determine whether or not curves like that are parallel.
I think if you're to address just the curvature alone, you can determine whether or not it's possible to have them mimicking each other, but then you have to go through more computations in terms of direction values. It could be a starting point, but it certainly wouldn't finish the answer to the question.
Alright.
I got an idea. Last time we met, I think I mentioned something, I remember I didn't prove anything. Didn't I mention that with a circle, there's constant curvature? But didn't I make the proclamation that the curvature is the reciprocal of the radius? Did I prove it?
Nope.
Sorry, I'll prove it. This is a math class, I shouldn't say anything about proving it.
Sorry, what was it again?
Curvature and radius, something?
I'm just saying, if you have a circle, whose radius is A, then I think the curvature is going to be the reciprocal of that radius. There's a very, really nice relationship between curvature and the radius of a circle. So, everybody, let's compute. To compute the curvature, all I'm going to do is compute, I don't know, which version should I use?
I'm thinking dt or ds.
You mean this thing right here? But isn't that merely t bar prime's magnitude over r bar prime's magnitude?
Or v's what again, sorry?
V, that's an r.
No, over on the,
Well, v is just a velocity vector.
okay.
And you guys, you might not be able to see this very well in the ink board, but that is bold-faced in my book. And so if I were to write that on the board, I'd have a bar over it, right? I just don't know if you can see that very well. And so you guys, let's come up with the equation of a circle in vector form. I said, you guys, let's come up with an equation for a circle in vector form.
X squared plus y squared plus
In
z
vector
squared.
form.
Doesn't that work?
No, not in vector form, it's just a scalar function.
Cosine of t, sine of t,
Times
times
times a.
times whatever your radius is.
Thank you, I agree. Do you guys agree?
Yes.
I'm
Yes.
feeling so alone again.
Oh, you said,
Well, except you have to, you know,
no.
if you're doing it in 2 dimensions, yeah, it's like that.
Never mind. I'll just shut up.
You don't have to be quiet.
It-
And you guys, if I were to compute r bar prime, what would I get?
Um,
Maybe sine t plus a cosine. Or an a cosine t, whatever.
Just whatever me. And I think r bar prime's magnitude is nothing more than, oh, you guys can do this off the top of your head?
A,
Thank you. Disagree.
yes.
Why? Oh, I get it. Okay.
Sine squared, cosine squared is 1, sorry, my bad.
That's quite all right. Just tell me, just yell at me. How can I come up with t bar?
Well, that's the
That's the-
unit tangent vector, so.
Unit tangent vector, so does it mean the same thing as this tangent vector?
Over A.
Yeah, no, I gotta divide by its magnitude.
R
Do you guys agree? But I think in this particular example, that's nothing more than, I don't know, is that just a negative sine of t? comma the cosine of t? Again, yell at me if I'm skipping too many steps.
Okay, so if we're doing
Okay, I skipped too many steps. My apologies. How about this?
So is there a reason why you started to put the magnitude in the numerator, but then
Yeah, it's,
that just looks really weird?
there's an random line.
There's just a random line in there.
Yeah, randomness just came in. I was gonna change it. Sorry. It is a vector.
Yeah.
Oh, I forgot something. Can I put it in? We just computed the magnitude of r bar prime. It's right above us. It's just simply a. It's just simply a, and my a's cancel. I think I'm merely left with what I had on the board before, which is this. Would you guys agree? And I maintain that t bar's derivative is going to be nothing more than, is that sorry, I'm so slow, you guys. Is that negative cosine of t?
Yeah.
Negative sine of t? Oh, by the way, t bar prime's magnitude then is going to be nothing more than one more. Oh shoot, we're done. That means I can describe the curvature as the ratio of the magnitude of t bar prime, which I just found to be 1, over the magnitude of r bar prime, which, oh look at that, it's just simply an a. So I've proven to you for a circle of radius a in 2 space, this curvature is nothing more than a reciprocal of radius. Where are you on the happy scale?
catching up.
3 out of 3 out of 11?
6.5.
A being the radius?
Yeah, a being the radius. What is a the radius here?
Yeah.
It's a 1 over the radius.
Can you repeat that last
So it's the
bit again?
magnitude of
After
t
you got
prime?
magnitude t prime equals 1.
Yeah, Matthew, do this. You see this one I have in green? It was nothing more than the magnitude of t bar prime.
Yeah.
But when you take a peek at this a that you see in red, I'm merely saying we've already computed the magnitude of r bar prime. It was right here in red.
How can you say that the curvature k is? Oh wait. Okay.
You sure it's okay?
Hold on. I'm thinking.
I'll hold on.
I'm thinking.
Can I start being sophisticated?
So, sorry. So okay, so that's the definition. Okay, and you plug that into the definition of the curvature. Okay.
All of a sudden, feeling a lot better about this.
Good, I'm glad. I guess I just needed to finish my discussion. Bless you. Okay, hold on. I need to think of an example that I actually do in a meaningful period of time.
Think of one that you don't know how to do.
Well, I don't know how to do the one I'm going to put on the board. Let's have it that way. I think this will work.
So this is a position function.
Yeah, and I'm just going to stick my, sorry, I can't speak today. I'm going to restrict my attention for a few moments just to 2 space. So do you guys think you could graph that in your head?
Not in my head.
Really?
Not in my head. I need a
Is
block.
it a cubed or a squared?
That's squared, that's cubed.
Oh, okay, I had it written down there.
Okay.
Worse.
It's worse. Thanks a lot. I was trying.
You know, we should just get like a digital board or whatever you can type stuff into to keep Eric happy.
Yeah, you know when I first moved to California,
Where'd you move from?
at that time, Montana. I got a job at Hewlett Packard. They had me go in there and I do presentations and there's no erasers. My very first presentation, I couldn't find any erasers on it. What do I do? And they said, well, there's a button on the wall. So I went to the wall, pushed the button. The entire board went into the wall. And there's a brush behind there. It comes back out, perfectly clean. So it was really slick. Here's your college. We don't have that kind of money. Would you guys agree with this? Would you guys agree with this? With this position function? Seems to me like the y components are getting bigger faster than the x components.
Yes.
Not quadratically, but more than linearly. And so I think in the first quadrant, I'd probably behave something like this. It's just that a t decreases without bound. I think my x components are still increasing like they were before, it's just my y components are all negative. I think it should look something like this. Would you guys agree?
And that's as t goes negative?
Yes.
Okay.
And I think a t being equal to, I don't know, how about 1/2? We can determine it. Both. I can spell both.
Is that, how did your O and your T become one? And is that an alpha?
Between you and
I mean,
Eric, stop writing, I'll just talk.
Just be glad you're not in the English department.
Honestly, the English teachers tend to have worse handwriting.
Actually, when I went to university, I was originally a language major, so I should be better.
I thought you had French, right?
Yes.
Curvature and the
Osculating circle.
the tangent circle.
Oh no.
what is an osculating circle?
It's that circle that touches,
The circle
that
that-
has
oh,
the
okay, that-
radius that's the same as the inverse of the
Yeah,
curvature.
okay, no, I saw that, yeah.
That cool, funky looking thing right there.
The one that I was about to ask the question on. Yeah.
Oh, is it really?
Yeah.
Okay. Oh, hopefully this will suffice.
Okay.
So this is a t equals 1/2.
So you guys just you prefer curvature in a traditional fashion. Actually, cheat. I'll save all these placeholders in the bar, on the board if you don't mind. For this particular function, where r bar of t is described as t squared t cubed, I said t squared t cubed. Let's compute. R bar prime is easy, is it not? R bar prime's magnitude, you guys, unlike the example I'm erasing the board though, check this out. Some of these values, or some of these functions I'm putting on the board are not constant. Because circle is easier, I had constant curvature everywhere. Here, I'm not gonna have that kind of case. That's why I had to make up a number for the t value.
So,
And, yes,
so do we substitute in t before we take the magnitude, or do we want to wait until the last minute to substitute it in?
I don't mind if you plug t in right now.
Mhm.
It's fine, you just couldn't stick it in originally because I need to be able to differentiate.
Okay.
And at least prior to differentiation process, you certainly cannot evaluate the R bar function at a given value t.
So by giving it a t-value, you're saying freeze at that specific point.
Yeah, and I'm being really lazy in front of the entire class today, you guys. I didn't graph carefully unitize my axes. And so I just made up a point right there. At least where the curve is described in terms of positive guys. I may have drawn my circle way too big. It might not have crossed the y-axis. I don't know. We'll figure it out when we come to the equation.
One more question, sorry.
Yes.
Does it particularly matter which side of the curve that osculating circle is going to be on?
Well, it certainly can't be on the other side because I've got to smoothly come into the curve with my circular portion.
Okay, all right.
It's
So,
always
so you
gonna be
can't
on
have them
the
going
inside
like
of
this. It's
any
always got to
portion.
be the same. Okay.
So if you have curvature as a parameter t, then the circle will always be like osculating as it moves around in time.
It'll be changing, yes. For every given point, your circle's not necessarily going to have the same radius. Certainly, for this portion of my curve from here on up, every single oscillated circle is going to have a different radius. Describe how the radii are going to change as I move along this curve. The radii are going to increase because the curvature is decreasing.
They're gonna increase because, okay. I see.
Because the curvature is decreasing.
Okay.
And since they have that inverse relationship that I've erased off the board, that certainly has to be the case. Eric?
How do you do the cross product when it's only in 2 dimensions?
Oh, what?
You add a 0 to the third dimension.
Yeah, you just lie.
Just lie?
Yeah, commit a lie, and just say the third component is 0. Makes sense, doesn't it? I mean, it's a logical lie because in your xy coordinate plane, the 2 space, you just treat the z component as being 0. So I think it's perfectly legal.
Okay.
So it's not really a lie. It's true.
Just a fib.
Well, but if I never told you z was, maybe you're parallel to the xy coordinate. Maybe you're in an xy coordinate plane that's diagonal in a whole new u, v, w coordinate system.
Okay, so as we approach a straight line, the radius of our circle approaches infinity?
Yes, I agree. As my curve gets more and more linear, then I think the curvature is going to get closer and closer to 0. I'll buy that.
Yeah, and that's just that k equals 1 over a. But yeah, way over there, right? That's exactly what that is. You're taking limits on
I
that.
agree. You guys, I'm kind of clunky today. I feel kind of uncomfortable with this because, again, I kind of was hoping Maddie would show me something different in her book. I think there are nicer formulas to use for curvature, but again, not a different definition. They come from the same setting, just a different derivation.
Yeah, because it looks like some of this stuff can be pretty handy if you have to remember it.
All right, maybe I'll redevelop it today for your take-home quiz.
I thought our quiz was in class.
Don't remind me. You guys, I haven't answered my own question yet. Can we come back? And so I think the magnitude of R bar prime is the square root of a
2t squared plus 3t squared squared.
so 4t squared plus.
9t fourth. Yikes. Okay. 9t fourth.
Am I doing okay?
Yeah.
And I think T bar is going to be, can I just stick a number? Yes, that's easier. It's okay.
You're saying when t equals 1/2, it's going to be?
See, I don't think I can. Because I think to come with curvature, I need to compute the magnitude of T bar prime. I gotta differentiate again. Do you see my point? I don't want to plug my T value in. So, I'll go in. My R bar prime is this. But I'm going to divide out by its magnitude, which is this. Or shall I say I've got this? You guys are starting so slow. I'm really tired. Is that a 2 over root stuff?
2 over root.
Comma. Be nice to me.
I just
Do I
thought
have-
that was funny.
Do you have a 3t over root stuff? Which I can't write. And now I want to differentiate. You know, I am right. This is kind of clunky. Maybe this wasn't a very smooth example, because now I got to use a closure. But we'll do it. I can't deal with it. I don't have enough room. Man. And I think to come up with T bar prime, differentiating component by component. Oy, oy, oy. Is it a negative 18t over 4 plus 9t squared to the 3 halves? Am I doing everything correctly?
Isn't the negative 1/2 on top, so the 1/2 on the top?
Cancel.
But wouldn't it be the 1/2 on the bottom?
Well, think of this as 2 times stuff to the negative 1/2 power. To differentiate it, bring the negative 1/2 down. Cancellation.
But the
Oh, you don't
exponent,
like that?
Oh, I'm seeing it. Never mind.
but then the exponent turns into negative, oh, duh. Never mind.
As long as you do it.
I was thinking it was positive.
And you guys, I gotta slow down. Shoot, I gotta use the quotient rule. For the second one, is that gonna be a, can we do it down here? To differentiate. Wouldn't that give me a root stuff? Times root of the top. Minus the top. Times root of the bottom.
54, what's that, t squared over blah, blah, blah.
Not seeing it.
54 t cubed.
I kind of lost the flow of things. What happened there?
I just differentiated.
Oh.
So I'm differentiating the bottom. The whole thing right here, which means I get the bottom times the root of the top minus the top times the root of the bottom. I'm missing a t on time.
Oh, you did a quotient rule?
Wouldn't, wait, what's that number on top?
27.
Isn't 18 times 3 though 54?
But there's a 1/2 in the exponent.
1/2 from the x component?
From
Yeah,
the,
from
from the
the-
square root is 1/2.
Oh, okay, okay.
Yeah, you guys just tell me if I'm making a mistake.
So this is t bar prime down here.
Yes, I'm computing t bar prime. I'm sorry I didn't write it. The error meant I'm going to differentiate. Can I just write it in? T bar prime's y component is this.
Oh,
Because I'm just differentiating 7 components.
Do you accept arrows on our work though?
the way, this ends up being, I have no clue, is that a 3, 4 plus 9t squared minus 27 t squared?
That is not a free fraction.
Oh, I made a mistake here. And then I get my 4 plus 9t squared to 3/2. You see, it's not pretty. Oh my gosh, it's gorgeous. It's just 12 over this.
Oh, okay.
Are my math 30 skills okay? Or your math 30 skills
Subpar.
okay?
No.
No.
It's too complicated.
No, it's not. It's very smooth flowing.
Is that the question?
Well, I remember I'm trying to come up with curvature. In Maddie, curvature, I'll interpret as a ratio of the magnitude of t bar prime to the magnitude of r bar prime. And I know I'm not there yet. I actually kind of come up with the magnitude of this vector.
We've already found out the magnitude of r bar prime, right?
Yes, we have.
So it's just sticking that big old sucker over that, and we're done.
I just need the magnitude of this piece.
And then we gotta plug in t equals 1/2.
Yes, I do.
So can you use curvature in the function of time to describe a given space instead of a vector value function? Because if it's like,
Can you back up and say it again? It's not just me, I'm tired.
can you use like k of t curvature as a function of time to describe a given space instead of a vector value function?
Well, curvature will never be a vector valued function. Curvature for free is going to be a scalar valued function.
Scalars or curvature is always a scalar.
No, I said scalar. You can describe curvature as a scalar valued function.
Scalar value function.
Doesn't mean it's constant. It just means it's a function like f of t equals stuff, no vectors.
Okay.
Because as you travel on a curve in 3, 4, who cares what dimensional space, the curvature is changing. But it's just a number that's changing. That's why I'm saying the curvature really is a scalar valued function as opposed to a vector valued function. Scalar does not take into consideration the direction of movement. To compute the magnitude of t bar prime, so I'm going to get a square root of this thing yeah, don't you think it's just too much work? Can I just cheat? Can I just now compute the magnitude of t bar prime e bat is equals, what did I say it was? 1/2, so I don't have to write all this garbage. Do you guys see my point? So, coming in, can I erase what's below, by the way? I can erase. Yep. So you guys, I just maintained this magnitude is of, square root of the sum of the squares of these components, but again, I'm just tired, I'm being lazy, I'll plug 1/2 in for t. I get a 9.